Superconductivity is an example of an intrinsically many-body quantum effect which doesn't really have a single particle counterpart, so it cannot be really understood based on just single particle Schrödinger equation. So in the context of superconductors, of course, these many particles are electrons, so that play together in some sense to create this amazing quantum coherent state. Now, to understand the very complicated array of many body quantum phenomena, the first step is to understand the concept of quantum statistics, which is an intrinsically quantum interaction between identical particles that doesn't really have a classical counterpart. So unlike, let's say, the electrostatic, let's say, Coulomb interaction, which depends on distance and between the two charges, so this statistical interaction between identical particles is quite different. It appears whenever you have identical particles and they feel each other's presence independently of the distance separating them. So this is very interesting. And so we're going to learn about it, and also we are going to learn about the two fundamental classes of particles with respect to their quantum statistics that are called bosons and fermions. And those guys, the lowest energy states, so-called ground states of bosons and fermions, are drastically different. And we will see that it's actually a transition in some sense from fermion-like behavior to boson-like behavior that is exactly what explains a transition from a regular metal into a quantum superconductor. So as the first step in defining quantum statistics, let us consider two identical quantum particles, these blue, represented by these blue dots here. And let's assume that all intrinsic properties of these particles are exactly the same. And so the question I'm going to be asking is what happens if we braid the two particles, or in other words, if these two particles exchange places. So the first particle goes to the place of the second one and vice versa. So what it means is that the wave function, so in this case the wave function describing these two particle system depends well on the coordinate of these two particles r1 and r2, and in principle some other quantum numbers that I'm not writing. And so the question we're asking is what happens with this wave function if you replace r1 with r2 and vice versa. So and it turns out that upon this braiding, the wave function acquires a quantum mechanical phase, so which is this statistical phase phi. And well, you can sort of get an idea of why it might happen, because the wave function really is a tool for us to understand the observable phenomenon. Most observables enter through the, let's say, absolute value of the wave function, or the various matrix elements of the wave function, and the overall phase is not really something that we worry about. And so we may imagine that even though from our perspective nothing has changed since the two particles are identical, which one is at which point doesn't really matter, so we still may in principle get a quantum mechanical phase here, and indeed this happens. Okay, so and so the question that we can ask, and that was asked a long time ago, what are the possible values of this quantum statistical phase? And the answer was provided in this seminal paper entitled "The Connection Between Spin and Statistics" by Wolfgang Pauli, who proved that there exists a one-to-one correspondence between the internal angular momentum of a particle, so-called spin, that you're going to learn about a little later in the course, and its quantum statistics. So I won't give you a lecture on spin because there will be a separate one on that, but I will just mention that there are just two types of particles allowed in nature, which have either integer or half-integer spin, and those differ by how their wave functions transform under rotation. So if we rotate our, let's say, coordinate system by a certain angle, so this rotation operator that we encounter would look differently depending on what kind of spin the particle has. And interestingly enough, let's say spin 1/2 particles, an electron is an example of such a particle, is going to be described by a so-called representation of this rotation, which upon rotating it by 360 degrees actually picks up a minus sign, as opposed to integer spin particles or particles with no spins that don't really change, whose wave function doesn't really change upon this rotation by 360 degrees. Now, I'm just sort of giving you a flavor, but the outcome of this so-called spin statistics theorem can be formulated in a very simple way. So for particles with integer internal angular momentum including 0, the phase here is really 0, so there is no change in the wave function. If we replace R1 by R2, nothing changes. While for particles with half integer spin, this statistical phase phi is equal to pi, or in other words, this psi of R1 and R2 is equal to minus of psi of R2 and R1, and these guys with half integer spins are called fermions. So I'll just make one comment that it turns out that this classification is specific to a three-dimensional relativistic quantum theory, to the world in which we actually live. But if we consider two-dimensional systems, which appear as a matter of fact in, let's say, condensed matter context, so we have two-dimensional metals and two-dimensional superconductors. So there, it turns out that the possibilities for phi are much more interesting. So apart from 0 and pi, we may have actually an arbitrary phase of phi, which are called, and the particles like that, so the fictitious emergent particles like that are called anyons, and even this phi can be a matrix, in which case they're called nonabelian anyons, but you know, this is the only thing I'm going to mention about it. But I just want you to know that apart from these well-known possibilities for fundamental elementary particles, so there are other situations which arise in condensed matter physics. But now let me focus on these two cases. So, we for regular particles, we have phi either 0 or pi. So let's assume we're dealing with fermions, let's say with electrons. So what are the consequences of this minus sign that we pick up in front of the wave function? Does it really matter at all? So should we worry about it? Now let us think about it. So what we're really saying again is that psi of R1 and R2 is equal to minus of psi of R2 and R1. And it immediately leads to a conclusion that for an important case of R1 equals to R2, so psi of R1 and R1 is equal to minus of psi of R1 and R1, which means that this psi is equal to 0. So what does it mean? It means that the probability of finding two identical fermions in the same point is 0, because psi is 0. So, it means that no two particles can be, no two fermions, identical fermions, can occupy the same point, and more generally, it turns out that we can actually generalize this for an arbitrary representation of the wave function. We can prove, and well, this is the Pauli exclusion principle, is that no two identical fermions can occupy the same quantum state. They cannot have exactly the same quantum numbers. But there is no such constraint for bosons. Okay, so this it has very important consequences. So this statement again is called the Pauli exclusion principle, and for bosons it doesn't apply. So the consequences are that if we have a certain quantum state, let's say an arbitrary quantum state I, and we want to populate this state with fermions, there are only two possibilities for the occupation number of this state. So the occupation number can be either 0 or 1. Well, for bosons, it can be anything. It can be any 0, 1, 2. You can put any number of bosons we want in this quantum state. Now, what does it mean in the context of many body systems when we have actually more than 1 and 2 particles, when we have billions and billions of identical particles, as we usually do in quantum systems such as, let's say, metals and superconductors? So let us discuss this question first for a many boson system. And what we're actually asking is what happens, let's say, if we have many energy levels that are initially empty, and we want to know what happens if we sort of pour identical bosons into this prescribed landscape of quantum states with some states I with some energies E sub I. And more specifically, what we're asking is, what we're interested in is what is the lowest energy state, the so-called ground state, that the system would want to form at low temperatures. So at low temperatures, the excitations are going to sort of calm down, and the system would want to form the lowest energy state. Now, since any number of bosons can occupy any state, so clearly the lowest energy state would correspond to essentially a state in which all bosons, non-interacting bosons that is, are sitting just at the lowest possible level. Now, for a free particle with dispersion, just having the kinetic energy dispersion p squared over 2m, some sort of parabolic dispersion. Here I'm just plotting it in sort of an example of a two-dimensional system, px, py, and this is the energy. Basically, all bosons would want to drop into the zero momentum state. Okay, and this kind of state is called Bose-Einstein condensate, a state in which a single quantum mechanical level, in this case the state with zero momentum and zero velocity, is macroscopically occupied. So this kind of phenomenon has been known for a long time, since Einstein, but it was sort of very observed in a clear way only very recently, in 1995 first. Now it's observed routinely in various laboratories, including our own Joint Quantum Institute. But back in 1995 it was new, and this discovery was actually awarded 2001 Nobel Prize in Physics. So here I'm showing the following. So basically what the experimentalists did, they trapped atoms, bosonic atoms, in a confined geometry in a certain trapping potential, and cooled them down to ultra cold temperatures, and then let them remove the trap and let them expand. And they just sort of took photographs of these atoms as time went by, and they saw this peak. So this is basically the so-called time of flight expansion, and this peak shows a population, a density of particles in real space. So you see that a large number of particles sort of don't move too much as time goes by, and this peak sort of in real space is a manifestation of condensation in momentum space. So this corresponds to particles with zero velocity, so they just sort of stay still. So now I'd like to mention a very important circumstance, namely that these Bose-Einstein condensates may host a very interesting phenomenon of superfluidity, where a condensate of interacting bosons form a superfluid which has exactly zero viscosity and which can flow therefore without resistance. So here, for example, I'm showing a photo of superfluid helium in a cup, and the helium can actually escape the cup climbing up the walls. So let me mention that superfluidity, the phenomenon of superfluidity, has actually been known for a very, very long time, since 1937, and it was discovered then in helium by Piotr Kapitsa. And Kapitsa got his Nobel Prize for this discovery in 1978. Well, a bit too late, 40 years after the initial discovery. So the mathematical theory of superfluidity was put together by Lev Landau, a famous Russian theorist, who got his Nobel Prize for this theory in 1962. So actually before Kapitsa. And let me just mention that this Nobel Prize was awarded to him after Landau got into a very serious accident. Everybody thought he would survive, but by some miracle he lived for a few more years, and this allowed the Nobel Committee to award him a long overdue Nobel Prize. So in any case, I'm not going to talk too much about the theory of this superfluidity now, because it actually requires understanding of the interactions in Bose-Einstein condensates, and this is a non-trivial business, interacting many body states. But I will just mention that superfluidity sort of rings a bell in the context of superconductivity, because if we want to explain the main property of a superconductor, namely zero resistance state in the superconductor, we would want essentially a superfluid of electrons, which would move with zero viscosity and without resistance. So this is exactly what the doctor has prescribed. But there is one little problem with this explanation of superconductivity, namely, well, electrons in a metal are not bosons. They have a half-integer spin 1/2, so they're fermions, and so they do not form a superfluid. So what do they do? And to answer this question, I need to consider the ground state of many fermion system now. We talked about the ground state of bosons. Now let me talk about what happens with fermions if I pour them into a given energy landscape. Let's say I have some available levels and I have a many fermion system that would want to occupy those levels. And the question is how I minimize the energy. So due to the Pauli exclusion principle, I cannot allow my fermions to be sitting on the same lowest energy state. So I can only, to minimize the energy, I can only sort of stack them up one by one to the lowest energy states as so until they reach the certain level called the Fermi level or Fermi energy up here. And basically this is the picture of fermion ground state, which is quite different from the bosonic ground state. Now, in the context of a metal, in three-dimensional metal, so what we have is, well, our energy landscape is given by the usual dispersion relation. The energy versus momentum is equal to p squared over 2m. So what I need to do in order to sort of satisfy the same picture with this energy is that I will occupy all momentum states. So here I have kx, ky, and kz, or I could have written px, py, and pz. So and below a certain momentum, which is called Fermi momentum, I will have all states occupied, just like I have here all these levels occupied, and above these levels are all empty. So and the threshold momentum is, just ignore these red and white dots for the moment. So below this threshold momentum, I have all states occupied. Above this threshold momentum, I have all states empty. And this is exactly the picture which describes electrons in metals. It actually works amazingly well for metals. And it's also known that the typical Fermi temperature in a metal, the Fermi temperature being this threshold momentum here, Pf squared divided by 2m, this is the Fermi energy, divided by the Boltzmann constant, which converts energy into temperature. So if we do this calculation, the typical Fermi temperature in the metal would be around 10,000 Kelvin. Which is huge. So even at room temperature, let alone at 4 Kelvin, so this energy scale is enormous compared to all other energy scales. So, and what the temperature, well, finite temperature usually does is that it excites electrons from below the Fermi surface. So for instance, I cannot excite electron from here to here. I cannot move. So this, let me just draw this process, and then I will say it's not allowed. So I have, let's say, an electron here. I cannot move it to this point. So it's not allowed. Because both the states are occupied. So this state is already occupied. So Pauli exclusion would allow me to do this thing. So, but what I can do, if I have temperature, I have some energy to spend. So I can excite an electron, let's say, from here to here. And so the white point here is an empty space that the electron leaves behind. It's called a hole, and the red one is the actual electronic excitation. And this is exactly the picture of a metal. And so these guys, basically these red guys and these white guys, these guys form, basically they are the main players in a typical metal. But they do not Bose-condense, they don't form a superfluid, they just move around and they experience scattering you know, from one point to a different point, and this results in a finite resistance. So how do we reconcile this picture of a metal with the presence of superconductivity that is observed at low temperatures? So this was again a major mystery for many years. It was not at all obvious how to do this, but of course there was a hint about due to the presence of superfluidity. So, and well, sort of in retrospect, it's pretty natural to ask whether or not it's possible to somehow convert an electron liquid, so this sort of so-called Fermi liquid, into a bosonic superfluid. So these guys are fermions, so they are not bosons. So can we make a bosonic superfluid out of a fermionic gas, such as here? Well, it's difficult, unless I allow my electrons to form composite objects of two electron states whose total spin is either 1 or 0. Remember, the spin of a single electron is 1/2, but if I combine the two of them together, so it's going to be an integer, so they were going to be bosons. And so if I somehow find a way to form such objects, well, I could have actually drawn it like this, but well, knowing the results, so I'm drawing these objects this way. But at this stage it doesn't matter. So if I allow the formation of two electron states, these two electron states are going to be bosons, and these bosons would be able to Bose-condense, and these guys would be able to form a superfluid, now a charged superfluid. And this is great because this state would superconduct. And this is exactly what happens. And these bound states of two electrons are called Cooper pairs. And from this perspective, a superconductor is a Bose-Einstein condensate of Cooper pairs. But the main question that remains is why these Cooper pairs would form. Why would such states appear? And this is the question that we're actually going to answer in the remaining two segments. And we're going to solve the Cooper pairing problem. And this will also establish a connection between this lecture and the previous lecture when we discussed bound states in weak potentials.